Hello, ma'am.
Hello.
Yeah, hi. Uh, Raksh Rakshita, not Rakshita. He didn't join now. Okay. Did serial in parallel out also completed, right? In structural modeling and behavioral modeling. Have you tried any other ways? No. I already given the program also in the group. Sumalata, did you gone through that session?
Yes, Prashanti, I have gone through yesterday's session and that
Okay.
serial in, serial out programs also I have gone through. The others I need to look it.
Okay, fine. Others we didn't discuss that. Today we will
Yes,
discuss
yeah.
on remaining parallel input, serial output, and parallel in parallel out shift register, bidirectional shift register, universal shift register. Okay, we will discuss on
Yes,
different models. I will give you some assignment also. You can look write some other coding because whatever we discussed till
sure.
now, structural modeling, behavioral modeling, those are very complex programming. Okay, like a structural modeling means it's nearly 20 number of lines code is there. So this is what we discussed in the last session. Here is a serial in, serial out, behavioral modeling, simple code, and also we discussed in structural modeling. This is what we write in a structural modeling. How many lines? Nearly 25 lines are there. Okay, but whenever we are writing for projects, any project like UART protocol or FIFO memory design. Okay, these registers counters are a simple, very simple block in the project level. Whatever we are writing here, particularly for the design, we are writing very complex, 25 lines, 30 lines like that. But whenever we consider in project, it's just a simple thing. Okay, so register counter, we do not write these many lines, even for counter also. We just need to write in a single line. Okay, suppose suppose where do we use? I will show you some example. There is a UART protocol. Okay, so UART protocol in the sense, first of all, what is meant by a protocol in a system on chip level or any communication purpose? We have serial communication and parallel communication. Okay, suppose there is a system on chip. Okay, in system on chip, there will be a processor and there will be some memory blocks and there will be some controller blocks like a DMA controller or DDR controller will be there. The graphic processor unit will be there, and also different IO peripherals like small keyboard or mouse, Bluetooth, and camera module. There will be a lot of GSM module, lot of IO peripherals will be there. Internal to this, there will be interconnections. Like processor need to communicate every block, every small component, it should be communicate. Like however our human brain is like a processor, right? However, it is communicating with every part of our body. It is sending the instructions to every part of the body. In the same way, the processor need to communicate to every part of the system, internal hardware. Okay, so the processor main central processing unit will communicate with the graphic processor, memory block, and also it communicate with the these controllers, and also it communicate with IO peripherals, even small wire connection also it will be communicating. Okay, so whenever processor is communicating with the block level like this, entire block level, mostly do the parallel communication through this interconnect. Here there is a interconnect. Okay, and through this interconnect it will do the parallel communication, but internally there will be small blocks. We call it as a IP blocks, or internal there will be a simple components like this. Okay, internal one component to another component, mostly we do the serial communication or even parallel communication. It totally depends on the specification, what type of specification we are using. Okay, and to the SoC, if you see laptops or mobile phones, there will be a ports. Suppose USB port for laptop, there will be a USB port. USB port is it's a protocol. Okay, so to the USB port we will connect a outside device like a mobile phone, or you can connect some like any power bank, whatever, some joystick. Okay, so this follow one type of protocol rule based on inter-communication system and intra-communication system. Okay, so if you observe here, two type of communications we can see. One is a parallel communication, one is a serial communication. Okay, so processor 2, I want to communicate with the keypad or some USB protocol is there. Okay, processor is communicating with the USB protocol. So processor always takes parallel data, and also it's a very high speed. It works at a high speed, high bandwidth. Whereas a simple keyboard, mouse, GSM module or Wi-Fi module, these work at a low bandwidth. Those are just a small IO peripherals. Okay, so for that purpose, we need to use the low communication protocol or low bus protocol, and here this side we use high speed protocol. Okay, and that too UART protocol or USB protocol, like this port type. We have I2C, SPI. So for serial communication, mostly USB, I2C, these all are serial communication purpose. Okay, so here parallel to serial conversion is happening, and here serial to parallel communication is happening. Whenever this USB need to communicate with another processor to your mobile phone, we send the data serial to parallel. Okay, serial to parallel communication is happening. So whenever we are doing here serial to parallel or parallel to serial, we store the data mostly into the registers. Okay, through the register, we will convert. Suppose here serial in parallel out is there. So serial in parallel out is one type of register. So here to convert parallel to serial, we use parallel to serial register. Okay, and here to convert serial to parallel, we use serial to parallel register. Okay, so in this case, actual block is a processor. Here actual block is a USB and internal IPs will be there. This parallel in serial out, serial in parallel out is just a simple connection. Okay, for that simple connection, if you write lots of program like 20 lines, 30 lines, it's like a very complexity will be increasing. Okay, so in these cases we need to write a simple logic just within single line. How can you design a serial in parallel out? How can you design a universal shift register, bidirectional shift register? We need to write a simple program. Even for counters also, in last session I have explained the counter logic, so where we use in real time. Suppose same in a protocol, from processor you are sending 128-bit data to the USB. Okay, so to count this 128-bit data, we use a counter. Okay, normally how the counter logics will be designed, like if you see like block level diagrams, this is what the counter block diagram, asynchronous counter or synchronous counter, whatever. So if you write in a normal way in Verilog programming, you need to design, suppose structural modeling, you need to design one T flip-flop and you need to take the copies of T flip-flop and make the connections. It also nearly 30 to 40 lines of coding you will be getting. But if you write that type of program here, it's not a good practice of coding. Okay, so this 120, our main task is to count this 128 bits, whatever the processor is communicating with USB with 128 bit data, we just need to count that. Okay, in that case, we need not to use these type of modeling, just a simple line, like how we can count 128 bits, okay, in a single line. Those type of coding is most required for registers and counters especially. Remaining all also we have seen different codes, but the register counters of any project, whatever the project you consider, mostly we will use everywhere, like a simple logic. Okay, so those things we will discuss today after completing these parallel in serial out, parallel in parallel out, bidirectional shift register, universal shift register. Okay, clear till here everyone?
Yes.
Okay, so parallel in serial out, I think serial in serial out, serial in parallel out, everyone clear? Okay, so next so parallel in serial out module. So how many number of clock cycles are required? Can you tell me? For parallel in serial out, if I consider 4-bit data, so at what clock cycle we'll get the output? How many clock cycles required at input side and how many clock cycles required at output side?
One in input side,
Okay,
4 on output side.
4 at output side. Okay. Any
No,
other answers?
4 in input side, 1 out side.
How can you tell?
Like parallel in, all are giving input parallelly.
Okay. Have you gone through the last session? I think you didn't attend it for the last session.
Yeah. Yes. Yeah.
Have you gone through that?
No.
Okay. Okay. So once go through that session and let me know why you are telling 4 clock cycles at input and 1 clock cycle at output. Okay.
Oh, okay. Yeah.
See, parallel means all data we are sending at a time parallelly. all data will be sent at a time. Serial communication means what? One bit after next bit, one bit after next bit, one bit after next bit, like this. So first bit, it will go at first clock cycle, second bit, second clock cycle, third bit, third clock cycle, fourth clock cycle, fifth clock cycle, like one by one bit. But parallel communication means as we are transferring all the data at a time, we will send all the data at single clock cycle, whether it's a 4-bit data or 8-bit data, even 32-bit data or 128-bit data. Parallel communication means at single clock cycle, we'll send all the data, we'll communicate all the data. Okay. So here for input, it just took only one clock cycle. To generate the output, 4 clock cycles are required. So 4 times shifting. And also I explained yesterday, shift and load operation here. Okay. So how we can write the program here? If you see, parallel in, serial out. So to load the data, 1 clock cycle. To generate the output, 4 clock cycles are required. Module, name of the module, clock, resetter, load, input, output. Load 0 or high, based on 0 or high, whether it load the data or shift the data. Okay. Next, input, clock, reset, load, and D input, output, D out, and temporary register. Why do we use the temporary register? To store the temporary data here. So D0 to Q0. Q0 is a temporary, and Q1, Q2, Q3. Here main output is D out. Remaining all these internal signals are wire signals. Okay, temporary signals. So if you see here, assign D out is equal to temp of 0. So last one is a temp of 0. From here, temp of 3, temp of 2, temp of 1, temp of 0. So last one is assigning to the D out. Remaining all are wire signals. Okay. So always at the rate of posage clock and negate reset. If reset is high, temp equal to all zeros. Else, if load is high, loading the data, all data input will be loaded into the temporary register. If load is 0, then shift operation. If you see here, shift or load bar or shift bar load. So load is high, loading the data. Shift bar is 0, shifting the data. So temp, for temp of 0, getting temp of 1, temp of 1, getting temp of 2, temp of 2, getting temp of 3, temp of 3, getting 0, first bit. Okay. So this is how we write the design program, and also we need to write the test bench. Okay. Clear everyone? Till here?
Yes, ma'am.
Okay. Rakshita, how many sessions you have completed till now?
4, ma'am.
Okay, we'll discuss at the end of the session. Okay,
Okay.
so how we can write in some more different way, like for parallel in, serial out, shift register. If you see here, another logic for parallel in, serial out, input clock, load, and data input 4-bit, data output single bit because serial in output, and temporary register. Always at the rate of posage clock begin. If load is high, then data is loading into the temporary variable or temporary register. Else begin, D out is getting temp of 3, last third one, because here we took 3 down to 0, so 0 is getting initially. Before one, how we took 0 initially, I mean 0 final value, 3 initially. Okay, totally depends on our design coding style. And temp equal to temp of 2 down to 0, comma 0 value. So it is shifting right. So how it is shifting right? Actually, temp is a 4-bit. Okay, but instead of taking 4-bit, 0 we are assigning here using the concatenation operation, and 2 down to 0. First 2 down to 0 will be assigned to temp, comma 0 will be assigned. So shifting right. Did you understood? Last bit. temp of 3 or temp of 0 assigning to D out. This is the last bit. Remaining T2 of 0, comma 0. These are shifting right side. Okay. And then D out will be temp of 3 is getting to D out. Then what will be the output? So left hand side is a test bench. You already know how to write the test bench, right? So run. D input, initially load equal to 0. So data is not loading here. And then D in is 1010 at this point of time. When load is 0, here when load is high, this data will be loaded, and D out. So when we get the D out in the next clock cycle. So in the first clock cycle, if you see here, D in 1010. Okay, till here load is X. So not loading the data. Here load is high. So in first clock cycle, from here to here, data is loading. Okay, so 1010. Data output also will get 1010. Not into the output, for temporary register will get 1010. Okay, next data out is getting. So this 1 0 1 0 output data. 4 clock cycles. It took 4 clock cycles. First clock cycle, second clock cycle, third clock cycle, fourth clock cycle, because output is serial. Okay, so total how many clock cycles from here to here? 5 clock cycles. 1 clock cycle at loading time and 4 clock cycles for shifting time. At this point of time, we'll get the output. This is temporary register just.
Can we limit the clock, Prashanti? I mean, till 4 cycles only. Clock is continuously.
Yeah, we can. You just need to stop the simulation there. You can terminate the simulation by using $finish.
Okay.
Here we just used at 100 time units, right? So you can use 50 time units or 40 time units. If you don't want to waste more number of clock cycles. See, like this. So D out 1 0 1. Okay, till 1 only we got. Then I need to extend the clock cycle. Suppose if I take 60 clock cycle. Okay, see D out 1 0 1 0. And number of clock cycles, 1 clock cycle, second, third, fourth, fifth, 5 clock cycles to get the output. Load is 0. When load is 0, shifting will be done. When load is high, it will load the data. Okay, clear everyone? Any doubts here?
No, ma'am.
Okay.
Ma'am, could you please explain the code once?
Okay. Here.
Yes, ma'am. The design part.
D out is getting temp of 3. Okay, suppose D out is the main value. Okay, so here what value we have to input side 1010. Okay, input equal to 1010, and how vector is taken here? 3 down to 0. D in is a 3 down to 0. That means the third bit, second location, first location, 0 location. Third location 1 is there. In second location 0 is there. In first location 1, 0th location 1. 3 down to 0. Okay. Now we are telling D out is getting temp of 3. So how we took here temp of 3? 3 down to 0. And D input also 3 down to 0. Same vector format. Okay. So D out is getting temp of 3. So this 3 is assigned to output. That means 1 is getting at D out. Okay. And then temp is equal to 2 down to 0, comma 1 down to 0. Actually temp whole data how much? 3 down to 0. Okay. So in the temporary variable, 2 down to 0 means 0, 1, 0 is getting, comma 0 is getting. Okay. So this is how it is shifting the operation. Now temp value is 4-bit data. D out is 1 bit. Okay. So here we get temp of 3 down to 0. So what is this 3 value? 1. What is the remaining temp value? 0, 1, 00. Okay. So here 1 bit will be eliminated because here we took extra bit to store full temp value. But here this value is full data out. Okay. In the data out, we will get, this is a main output, remaining is a temporary value. Okay. Same if you see the waveform, how it is shifting. Okay. So initially this 0 will be shifted to here, and this 1 will be shifted to here, and this 0 shifting to here, 1 is shifting to here. Okay, clear?
Yes, ma'am.
Any other doubt? And here also same. You can write the simple test bench and check here. Okay. If both are same variables, I can check now only. Load clock D in. There is no reset. Clock load D in, D out. Okay. I'm changing the names here. D in, D out, or else directly we can write other names also. And here D in, D out. Okay. And here I'm considering the reset also. Or STR. Okay, reset. So here if reset is high, temp equal to 0. If load is high, D in. So initially here I'm taking reset equal to 0. By default 0 I'm putting. Okay. Save and run. What are the errors? 6th line test bench. Okay. In port connection, now we need to mention reset. error. Okay. Here design name DUT connection. We need to syntax error at design tool. Okay. Need to comment this. Syntax error at 6th line, test bench 6th. Comma. Waveforms not open. No? Okay. EP waveform. Open EP waveform and run. One zero 1 0. Load is high. Load is 0. When load is high, D input is loading and load is 0. So 1 0 1 0, shifting the data. Okay. Is it clear? Everyone? Parallel in a serial out. Total 5 clock cycles. In first clock cycle, loading the data. Second clock cycle, 1 bit shifting. Third clock cycle, another bit to fourth clock cycle, and the fifth clock cycle, next bit. So total 5 clock cycles. Clear? Hello?
Yeah, ma'am.
Any doubts? Okay, so these are the two models in parallel input, serial output shift register. And then next example, serial parallel in the parallel out. So parallel in parallel out, very easy. So how we can write parallel in directly? We are loading the data parallelly to the flip-flops and getting the data. Okay. So it's very simple program. So like this module, parallel in parallel out, input output declaration, always at the rate of positive clock, Q equal to D. So whatever the D, whether it's a 3-bit data or 8-bit data or 16-bit data, whatever, directly D is loaded to Q. So you can check the diagram. All B data is loading to Q. So that is how we can write in a behavioral modeling. If you want to write the structural modeling, again you need to create the D flip-flop, need to make 4 copies of flip-flop. Same however we written here in a serial input parallel output, writing 1 D flip-flop and making the copies, same you need to write. Okay, but these are not preferable. Okay, we need to prefer like this only, simple coding style. So run. See. Total how many clock cycles will it be required? Can you tell me? So for 4-bit shift register, parallel in parallel out, how many clock cycles are required to load the data and to get the output?
2, ma'am.
2 clock cycles,
2.
right? Parallel side, both are parallel only. So input side 1 clock cycle, output side also 1 clock cycle. If it is a serial, based on the number of bits, it will take number of clock cycles, as you have seen in the serial out. 4 clock cycles we got. But here parallel out, single clock cycle enough. Okay. So if you see the waveform here, so initially 3 down to 0 x. So at what time we took the input values? Initially clock equal to 0. At a 10 time unit, D equal to all ones. Next 20 time unit, D equal to 1010. So that's why initially it's a 0. At 0 simulation time, initially all are X. At 10 time units only, all are ones. So D in all ones. Next, at what clock cycle all our output is getting ones here. Next, loading 1010 and getting the output here. Okay. Within single clock cycle, both input and output are getting always at the rate of pause H clock Q equal to D. Triple one and the positive edge of the clock, so getting the output. But it's wrong. At negative edge of the clock, D is getting assigned with 1010, and here also at negative edge of the clock, 1111 is getting assigned, and here it is okay, getting correctly. X is okay. At assigning time, it is taking more delay. Why it's taking more delay? Q equal to D at positive edge of the clock. Initially, all ones at suppose if we take the reset clock D. In test bench also declare the reset value, and in DUT also declare the reset value. So initially reset equal to high at 10 time units. Reset equal to 0. No. Reset equal to high, so output is 0. Reset is 0. Triple one ones. Actually, here itself it should get the data positive edge of the clock. Okay. Still getting the same. Okay, we'll try in some other way. In asynchronous, where we can try. Here I'm just taking the passage. Reset. If reset is high, q equal to q equal to 0. Okay, still getting the same back. Okay, I will check this once again. Why it's not getting for this logic. We will try with some other logic. Okay. Till here, everyone clear? From your side also, once try with this. Okay. We will try some other logic. Okay. Hello.
Yeah, okay. Priya.
Next, bidirectional shift register. So for bidirectional shift register, we can write in structural modeling like this. So how can we write the structural modeling? Same, however, we have written for serial in, serial out shift register, serial in, parallel out shift register. We can write the structural modeling. So first we need to create the D flip-flop and then 1 2x1 multiplexer. By using the D flip-flop copies and the multiplexer copies, we can design. For bidirectional, we will write in the structural modeling. For universal shift register, we will write in a behavioral modeling, the simple code. Okay. So if you see here, this is what bidirectional shift register, and here one multiplexer program, Muxer 2x1. You already know how to design the multiplexer in a single line and flip-flop in a single line. We don't need to write the complex programs. If it is a 32x1 multiplexer or 8x1 multiplexer, we can write in a array model. Most of the cases we used array model only, right, for hierarchical multiplexer. But here we have to conditional operator. Y is equal to, if select is high, then D1 will get assigned to the output. If select is 0, D0 will get assigned to the output. So it is just a conditional operator. And D flip-flop also very simple coding. No need of writing reset and all. Okay. So Q equal to D. So if you don't want to write in this way, whatever we preferred before for serial in, serial out, here this D flip-flop using the clock clear signals, you can also use this code. Okay. So totally I have given 10 models for multiplexer and for flip-flops also. You can use any one. and next shift register. So total, finally at top level, how we are going to connect each one. So multiplexer we have connected and need to take 4 copies. D flip flop also need to take 4 copies. So here if you see multiplexer 4 copies, D flip flop 4 copies. M0, M1, M2, M3, D0, D1, D2, D3. And what are the selection lines? So if you see here, what are the selection lines left by right bar? Okay, bidirectional means it will do the left shift operation and also right shift operation based on the signal L by R bar. R bar in the sense it's a active low signal. When will be active low signals are activated is equal to 0. Whenever it is equal to 0, then it do the right shift operation. Whenever it is equal to 1, then left shift operation. Okay, so if I show the output here, the shifting operation, how each one is connecting. Suppose here serial input is there. Okay, and here also serial input, right side or left side. Suppose if equal to 1 means what? Left shift operation. Left shift operation high means selection line. If left shift operation is high, it's a 1. Then how it will be connected? This Q2 output is getting to here. Okay, so Q2 is connected to here. And here also left shift equal to 1. That means Q3 is output is getting. But where we get Q3? From here. And here left shift equal to 1. So Q4 is connecting here. But where we get Q4? From here. So if you observe properly, from here the data is shifting left and getting here. And from here data is shifting left and getting here. And here the data is shifting left and getting here. And final output will get here. Okay, from D4 to D3, D3 to D2, D2 to D1, left shift operation, L equal to 1. In the same way, if R equal to 1, I mean R equal to 0, then what output will get? So if you see here, SI will get here. Okay, so here SI 0. 0 means this serial input is getting to D1, and here again 0. So Q1 is getting here. Q1 means directly this value is connecting to here. Again 0. So Q2 is connecting. Q2 means this Q2 will be connected to here. Again it's a 0. Q3 is getting the value. So Q3 means this one is connecting. So if you see properly, it's a right shift operation from serial input to first flip flop to second flip flop to third to fourth. Finally, we get the output at this point. So bidirectional shift register. How you can implement in a simple logic? You need to take 2 shift, left shift or right shift. Simply we can write in a simple shift operator. But in a structural modeling, how we can write? So this is what structural modeling. So took the copies of multiplexer and D flip flop and make the connections here. You already know how to make the connections. Okay, so run the program. So here, I mean test bench, shift register DUT, creating the clock and initializing with the input values. Okay, so what is a serial input, and if left or shift LR equal to 1, then left shift LR equal to 0, then right shift operation. Okay, so click on run and you can open waveform also. Click on open waveform and here need to write the dump file, or else I can copy from here. Okay. So Q serial input x, here we took x actually. So if you see here, at 0 simulation time, or equal to 0. Or equal to 0 means what? Right shift operation. So serial input equal to 1. Initially q equal to all x. Output equal to all x because no output is getting. Or equal to 0, right shift operation. So s equal to 1, right? So that's why 1 we got, remaining all are x. Again, like this, 1 x, next 0 x, and right shift equal to 1. That means it shift left. So 0 1, and here it will shift left. So this 0 will be assigned to left, and here also again left. So that's why we got 0 1. This 1 is getting to assign with left, and here 0 1. So this 0 is getting here, 1 is getting here, and 0. Serial in is 0, right? So from left right side onwards, this serial in will be assigned to left. Like that the shifting operation will be happen. So whatever the serial in is their value, it is assigning to left. And here serial in value is 0, so assigning to left. And here right shift operation, this 0 will be assigned to right. So if you see here, 0x 0 1, and here again 1 right side. So 1 0 x 0, and again here. Okay, like that. It takes single clock cycle to reflect the value. Clear, everyone? Based on here these values, you need to check 0 1 0 1, left shift or right shift. I will share you the codes. Once go through the code and try to understand. Okay, or else simply if you see here, all zeros and all ones, SI ones, all ones are right shifted. Here one right shift, and here also this one right shifted, and here also this one right shifted, and here also this one right shifted. Okay, like that. Here all are ones. That means left shift. If you observe properly, from where x 0 1 x x, this x will be left shifted. See, this x will be left shifted because serial in is 0, right? So that's why 0 is assigning here, and again this x left shifted, and here x si is a 1. So that's why here si is 1, and here again si is 0. So that's why, based on the values, if you don't change these values, if you put standard in this way, you will get understand more easily. Okay, clear? Bidirectional shift register.
Yeah, ma'am.
Others, what about remaining?
Yes.
Yes.
It would bit confusion, but try to understand after the session. Another bidirectional shift register in a simple way. Okay, bidirectionally shift right or shift left. So if you see another type of programming here, input clock select load, because multiplexer have the select signal, and input D, output Q. Okay, always at the rate of pause at clock. If load is high, loading the data, Q will get a D value, loading the data. Else based on the select signal. So if select is a 0, right. If select is 1, left. So same here. If select is 0, left here. Okay. Select equal to 0, load equal to 0, select equal to 0. Okay, it depends on your design. You can also put, if select is equal to 0, then left or right. You can just simply put right also here. And if select equal to 1, left. Okay, so if we write the program, if you do the run, so D equal to 1, D equal to 1, load is high, loaded the data, and select the signal. Select the signal is a 0. Select signal is 0 means left shifter. Okay. So that's why 1 is left shifted to here. 1 0, 1 triple 0, 1 1 double 0, 1 triple 0. Shifting left. See, initially it is a 1 triple 0. No, initially it's a 1. Wait, I will show here. Initially 1. 1 means how much value? Triple 0, 1. Next 1 0. 1 0 means here we get the value. Remaining these two will be 0. Next 1 triple 0. So 1 triple 0. Next 1 double 0. 1 here 1 double 0. So if you observe here, all ones are left shifted. Okay. And select equal to high. Select equal to 1 means right shifter. So right shift means this 1 triple 0 is shifting right. 1 double 0. 1 double 0 means 0 1 double 0. Then 1 0. 1 0 means double 0 1 0. If you increase another clock cycle, you will get as a 1. 1 means triple 0 1. So right shift operation. Okay. So this is how we can implement a simple bidirectional shift register, and also you can take SI value. Based on SI value, how you can control the signal, you can consider that. Clear everyone till here? Structural modeling and also behavioral modeling. Mostly we will consider this only, this type of programming only. Okay. Any doubts? Lahari, Rakshita, Sai, Suma, Sunny, Vinita, Venkat.
No, ma'am.
Okay. Now your task is to work on universal shift register in structural modeling. However, we design for this bidirectional shift register in structural, you can design universal shift register in structural modeling. Okay. Bidirectional shift register means only two functionality, just shift right, shift left. But universal shift register means we use 4x1 multiplexer with 4 functionality. 0 0 means a no change. No change means what? Loading whatever the input is there, output will get same data. Next output will get same data. Next 0 1 means shift right, 1 0 means shift left, 1 1 means parallel load. Same like this, you can write. You can take the selection line as a 2-bit size. 0 0 no change. In flip-flops we write the no change condition, right? So q equal to q value, like that. So no change condition. For 0 1 shift left, for 1 0 right, shift right, for 1 1 parallel load. Parallel load means q equal to d. That is what parallel load. You can write in a behavioral modeling, and also you can write in a structural modeling. Same structure. Create a 4x1 multiplexer and D flip flop and make the connections. Okay. Clear till here, everyone?
Yes.
Okay. Now we will design some codes, like simple codes. We will start from this one, universal shift register. Okay. So how we can design universal shift register? in a simple like logics. I will tell you logics only, but try to implement from your side. Okay, so universal shift register is there. Mode signal. First of all, we will consider the mode signal, or we can also call as a selection signal. Here, this one we can call as a selection signal or mode signal. Okay, so I'm considering clock, selection signal, and also serial input signal and input, parallel input, output, Q. So declare all the input and the outputs always at the rate of POSH clock. And if I put POSH clock and negate reset or POSH reset, what is the difference between those two? Can you tell me? What is the difference between, suppose I am putting POSH clock or negate reset or even POSH reset also? What happens if I put like this, or if I don't put anything? Q equal to no change. That means Q. Okay, memory state, or else you can tell like holding the data. Okay, next to 2-bit binary 0, 1. So 0, 1 means what? Whether shift right or shift left? Shift right. So how you can write shift right? Not simply like a right shift operation, however we put in a bidirectional. You can try some more different way. Shift right means based on conditional operator. Before we have seen the conditional operator, right? So shift right means what? Whatever the serial input is there, that should be shifted towards right. Okay, so serial input always be left side and Q 3 down to 1. So whatever the 0 is shifting, 0 value is there, that would be shifted right. Okay, so that would be getting the it's a loop rotate operation. Okay, so it will be in a SI position, 4th position, and then Q 3 down to G1 will be the towards right position. Okay, so that is what shift right. 2-bit binary 1 0. 1 0 means shift left. Shift left means how you can write a reverse of shift right. Shift right, we kept 3 down to 1. Here we can mention 2 down to 0, comma. At the 3rd bit, we will add shift in. So shift left value. So shifting towards left. Okay. And then final one, parallel out. Parallel out in the sense just getting the input value, whatever D or P, whatever the parallel data you will be loading here. This is how we can design universal shift register in a simple way. Try yourself. Okay. Clear, everyone? Next, for serial input, serial output shift register, another logic. So whatever we have discussed till now, other than that, other than structural modeling and behavioral modeling, how we can write here? Suppose input I have considered as a serial in, output I have considered as a serial out, and also I have declared the reg shift value. Suppose something temporary variable. Okay. So I am writing always at the rate of POSH clock. So how we can take, suppose for temporary register, same right, like this we can assign, right? Shift right in the sense shift reg 2 down to 0, comma SI. So to the temporary register, shift reg. And S naught. What about S0 value? Si. So this S naught output. Output should get main output reg value. Nothing but temporary value. Temporary of 3. Okay. Did you understood everyone? Third bit assigning to output. Remaining all are shifting. Like that serial in parallel out. So parallel out means simply directly we will get the output but shift. Suppose how we can write serial input parallel output PQ. PQ equal to parallel output of 2 down to 0 comma Si. If I don't take any temporary register, directly I am shifting P2 down to 0. Is that correct? Parallel in a serial out. Sorry, serial in parallel out. Parallel out. Serial in a parallel out. Serial input, I'm just taking one input here and that input will be shifted. Parallelly output is loaded. These all are temporary registers. So Q, Q3 and here all are parallelly loaded and last bit I'm considering in this way as I. Next serial in parallel out. Same serial in parallel out, the reverse operation of this. Okay, just take these inputs and also I have shared all the ports yesterday and the remaining also I will share and try differently. Okay. In the next session, we will discuss on counters, asynchronous counters, synchronous counters. Counters also most important thing. We have good assignments on counters, like how to design a 3-bit counter with 2 input clock cycles and counting multiples of 3, skipping multiples of 3, and free running counter, how to mask multiples of 3 between the range 0 to 100 or 0 to infinity, and how to count multiples of 5 between 0 to 100 range and masking the multiples of 5, and up down counters basic only, and design a counter for like counting 4 ones, 4 twos, 4 threes, 4 fours. We will discuss till here. Okay, not in the next session. Next session, digital electronics theory part. Once theory is completed for all these counters. Asynchronous counter, how to design this, and up counter, down counter. In asynchronous negate, we need to consider negate and posage. And synchronous counters, up down counters. First we will see in a structural way, same like registers, then we will try to write a more logical way. Okay, so till then counters will complete, registers counters by this week, mostly next week. And then final state missions. Clear everyone? Any doubts? Lahari, Sumalata,
No question.
Sunny, Sai,
No.
Rakshita, Sai, and Sunny. Still, how many sessions are left?
4
sessions.
ma'am.
4 sessions. Did you got the answer yesterday? I have asked, right? So what are the conditions for procedural and continuous?
Yeah.
Have you completed that session?
Yes, ma'am.
Did you got the answer?
Yes.
Okay. Vinita, any doubts? Venkata Krishnam Raju, any doubts? Okay. So one
I'm
day
not
we will
able to
discuss
understand the session actually. So, because
Okay.
I don't have the understanding about this system Verilog.
It's not system Verilog, it's a Verilog only.
Yeah, okay. So, these basics, because I'm not familiar with the basics. First time I'm just seeing that code and then
Okay.
workbench.
Okay.
So,
Fine.
I need to get that first before getting into this. I need to get familiar with this basics.
Okay. Yeah. Okay. What about others? Okay, fine. I'll share you the recorded session and also the coding. And also I will share the assignment on registers. Did you completed assignment 2 in Verilog? Problem statements.
Only till assignment 1. I think.
Assignment 1 completed, huh? Okay, fine. Okay, then we'll see in the next session. Okay.
Yeah, Prashanti, can you tell that how the integer values can access in Verilog?
Integer values can access in Verilog.
Yeah, I mean like number direct 2, 3, some. For example, swapping the numbers. If I take a equal to 5 or b equal 10, like that, directly access the integer value.
Integer data type is there in Verilog. So whenever you are creating it as a reg data type, suppose here reg is there, right? D reg 3 down to 0 D. So you can consider it as a integer D. Okay. But integer
In
is a
test bench,
default.
it is taking Prashanti. In test
Uh,
bench, it is working, but in the design, I'm
Design
not
it
able
will
to.
not work. Integer is
Yeah.
not a synthesizable. Integer
Yes.
real time
Yeah.
is 3 are not synthesizable. You